Good morning, good afternoon, and good evening. Welcome all of you to the live program number 146 at Orthopaedic Principles. We are back with a phenomenal faculty, Professor Justin Cobb from the Imperial College, London. Justin is chair of Orthopaedics at Imperial College, where he runs the MSK lab in the Sir Michael Urin Biomedical Engineering Hub, with 12 floors of clinicians, engineers, and scientists. The focus of his work has been on ceramic and ceramic hip resurfacing, assistive technologies, robotics, 3D printers, and enhanced reality headsets. After training in Oxford and London, Justin was consultant orthopedic surgeon at the UCL from 1991 to 2005. He was appointed to the King Edward VII Hospital for Officers in 1998 and became the orthopedic surgeon to Her Majesty the Queen in 1998. Today, Professor Justin Cobb is going to discuss about 3D printing in orthopedic surgery. Over to you, Prof.
Okay, thanks, Satish. So I'm going to talk a little bit about how 3D printing impacts on all of our lives. And starting with where we are right now, which is we're part of, well, all the arthroplasty surgeons, we're part of this huge vehicle, the total joint industry. And it's, I guess in the subcontinent, it must be 1 million hips and knees a year, maybe it's more. Huge volumes of people in part of this total joint replacement industry, each of which costs more than a new car. And certainly in the UK, we have had no productivity increase since John Charnley was doing hip replacements in 1965. So all this time later, no increase in number of cases per day. It's a big operation, long stay, high cost. And I hope I'm going to persuade you that with the additive layer manufacturing revolution, we're going to upskill the surgeons doing smaller, precise procedures, better quality, better quantity. And so the societal cost will be lower. And here's a case I will come back to of a man with a malunion of his tibia from his school days with medial compartment arthrosis, and there's been a metal inside him. We'll come back to that as a problem. Now, any additive manufacturing relies upon imaging, about 3D imaging, and these days axial imaging is easily available, and the reconstruction of this axial imaging can even be done with a processor on a mobile phone right now. So really there's no excuse for arthroplasty surgeons not to use precise planning as part of their surgery. I'm very lucky to have Simon Harris working with me. Simon, I've known since about 1990, in fact. He was writing an operating system for our first robot in hexadecimal code, including the entire GUI. And here he is planning a tri-compartmental knee replacement. You couldn't do this without planning, or rather, I think it's a better idea to plan. Here's Farhad and Ed, and they're looking at tracking and pressure of tracking. Again, something of how the patella loads up in health and disease. Something you can't really do without good 3D models. This is Martin, and he's looking at the shape of a knee. This is actually a knee that's had a high tibial osteotomy. They're having to undo it. And he's looking, using a 3D model, allowing us to plan surgery, seeing where the best place is for the osteotomy. These are things that you simply can't do. Well, you can do it in 2D with a China graph pencil, but it's a heck of a lot easier with good imaging. And it's really a pleasure to work with those guys doing that stuff. Here's an example of a man from 7 or 8 years ago, where we actually imported his gait data from the gait lab into the planning. And you see this is a very deformed femur, and we did a series of different operations, seeing which was the best to try and get his knee sort of underneath the shaft of his femur, what was possible to do. And then Susanna Clark, another brilliant engineer in our group, made these beautiful renderings preoperatively. So we went through the whole operation with her preoperatively, doing the arthroplasty cuts in completely the wrong place, of course, but they'd been made the right place by the osteotomy cuts. So we printed the instruments that she planned, and then having done those cuts and put the trials on, we then did a closing wedge and an opening wedge, simultaneous osteotomy, all beforehand. So she did all the surgery beforehand for us, including bending the plate. And then intraoperatively, we simply did exactly what she planned, which one wouldn't have dreamt of doing this without 3D planning and printing. And it looks like a great big operation, but every single step went fine, and I've walked around a golf course with him. It's a really amazing planning technology that allows you to do stuff. Now, just a word about the devices we use, and I think we're all used to this amazing history of the last 60 years from bits of stainless steel that genuinely, those bits of stainless steel broke, and the cobalt chrome castings were much more durable. Really, that did change things, no more until really failure of the prosthesis wasn't a thing really after the cobalt chrome came along. But the large monolithic bits of titanium even are so much stiffer than shorter bits. Ed here in the lab did a nice little study showing how the fractures, how if you have a shorter stem, you have a much more flexible femur maintained, and a longer stem, much stiffer femur. So but then if you're using that titanium more cleverly, Jonathan Jeffers, Richard Van Arkel, this is their beautiful Renshaw 3D printer, that's JJ, and they can print titanium now, not to have the structure of monolithic titanium, but to have any structural stiffness they want. And just recently, we had a brainstorming a couple of years ago saying, let's reinvent the screw. And what they came up with was a solid piece of titanium that actually has a shell on the outside, a solid core, and these fibers, so these are two separate pieces, but they're actually printed together like this. And the push-out strength here, that's pushing in, and that's trying to pull out. Huge difference in the force needed. And as the strut density goes up, huge difference in the force needed. So this is a real one-way device, like a roll plug, made of titanium. Really a lovely bit of sort of engineering. Here it is in 2D. Here is a picture showing you the actual structure in real life. And here's, I hope this runs, and here's a video of Richard with two of these, just pushing these into foam. He's literally just pushing them in with his hand into some foam. He's a very good engineer, by the way. And he's backing himself. So he's a skinny guy, but still these have got good resistance to pull out. So titanium, actually prosthesis design, that's not 3D printing, but prosthesis design will definitely be transformed by playing around with the material properties, not of actually the titanium itself, but by the way you print it. Now, PSI Guides, I think, are the other things that most of us think of when you think of 3D printing, and they definitely allow you to deliver a quality that you just couldn't do otherwise. This is Susanna Clark's group. She's really a phenomenon, designing guides where most of it is modular, but a very few bits aren't. Here's the printer printing bits of, and here's Paddy, but this is a PSI knee in a box. The box is printed as well. You get a model and you get instruments that really only let you do it right. So it sticks onto it holds on the malleoli outside the skin, and then inside a very, very small footprint inside the bone. And those two alone allow you just to cut out the tiny bit of bone that you're taking out and make sure you cut it out exactly right. And the same on the femur, it just sits on the femur, part inside, part outside. So that family of technology really has, at very low cost, allowed us to achieve our plans for every case, if you like. And this is actually one of the very first cases we did. This is 9 years ago now. A man with a straight tibia, but a very deformed femur from childhood. He was hit by a lawnmower as a child, so very varus. They'd have tried a corrective osteotomy of his tibia, but he had this varus femur. And of course, the maximum angle of deformity is not in the coronal or sagittal plane. It's always a skew plane. And Susanna designed the guides to allow us to undertake this osteotomy, which again, I just wouldn't have tried this as a skew plane osteotomy. One wouldn't dare do this without guides, but it worked perfectly. It's 9 years later, he's still skiing, very active man. One more difficult case, this is a difficult case. He's a young soldier. He was shot in Iraq, horribly deformed man in his 30s, very depressed, a very deformed leg now, having been in a fixator for a while. And so, because he was a young man, we really threw the book at this, flipped the good leg onto the bad leg. And then again, Susanna designed correcting the osteotomy on the femur and made a custom-made plate so that we then had the femur straight again rather than deformed. But then, having got a straight femur, we then had significant loss. So we had to design a lateral femoral condyle replacement of titanium and a proximal tibia with really very poor soft tissues, where he really lost his proximal tibia on a little buttress here. And then intraoperatively, we used a little robot, in this case, to sculpt away the bone, very, very bad soft tissues where the shrapnel wound had been. But really doing a precise procedure. I would never have dreamt of doing this without assistive technologies. And here he is a few days post-op. And if we're lucky, yeah, so really a nice straight leg. He now works as a chauffeur. He's back, as it were. So young people, you can really spend a lot of time and effort reconstructing them. I'm sure it's not the last operation he's going to have, but he's still got his cruciates, which is interesting. And then finally in the hip, just a little bit of fun really. So in the hip, in the femur anyway, with just a single tiny piece of plastic that just fits exactly here, if that is where you've planned your brooch to go exactly, then you know you're going to make your osteotomy precise. That's the guide for your brooch, so you don't get varus valgus errors, you don't get leg length errors. So this single bit of plastic completely transforms femoral preparation. And actually, even the Mako robot can't do this at the moment. And here's a deal, one of my fellows, a couple of years ago now, he's one of those fellows with a bit of a temper who, if he doesn't work, he tells you. Anyway, so here he is, just, you'll see he's got a single pin, and he's just making sure this sits perfectly on and is clamped on firmly with a little shanks pin. Once that's on, then the rest of the operation is, honestly, it's over. There's one extra little instrument he's got to help him with this. Oh, he was blindfolded. So this is a bit of plastic that upskills surgeons, allowing surgeons to achieve their plans with a very low cost, a little bit of 3D printed nylon. And I guess the last element of this is a whole set of 3D printed instruments. So one of the problems that some people find, certainly we find, towards the end of the day, sometimes all the instruments have been used up. And sometimes in some parts of the United Kingdom, instruments have to be sent far away, far from the site to be sterilized. And the cost of these trays and trays of instruments sitting there is great. Somebody has to bear this cost. So as part of our HIP project recently, Rob Wozencroft set about designing an entirely 3D printed single-use set of instruments. So single-use reamers, single-use femoral head tools, all completely throw away. And actually, if you do of course, it seems like, well, this is a very expensive way of doing things, but if you actually cost out the cost of trays of instruments sitting on your shelf, they're pretty high cost too. And this is certainly something I think we're all going to see more of. If you've got a very precise tool, you can achieve an astonishing, you can achieve great economy and very high quality surgery just with very smart instruments. And the single-use patient-matched instruments, I think, is a sort of additional bonus that you can actually now have instruments as part of that single-use set, just a couple of them patient-matched, and then you've got a set that's really delivering a very interesting product. And I think it may even be cheaper than having sets of instruments sitting on shelves, obviously slightly depending on several factors. So that's a sort of overview, I suppose, of the range of technologies. Just go back to that case I showed you before, because this is a man who we did just before lockdown. So he's now 59, I think, and at aged 11 or 12, he was hit by a car with his short bent tibia rather, and a very bad medial compartment. And so of course, Martin looked at the deformity, looked at the size of the deformity, saw, and so we did a 10-degree opening wedge osteotomy of this upper tibia, because the plate was completely in the middle of the femur, of the tibia. To take that plate out and do the corrective osteotomy there, I've done that. It's very, very stressful doing that. Very stressful. So we did this in the sort of native tibial metaphysis, and having done the corrective osteotomy, got his medial proximal tibial angle down to a really pretty reasonable number there. And then off we went to the operating theatre. And here's the surgery, and the operating theatre with a PSI guide. I didn't put the pictures in, but with a PSI guide to do the osteotomy and the uni in the same sitting. Of course, you'd never dream of doing just the uni, doing it wrong without the PSI guides. The only change I made actually from this plan is you can see the hinge point here. I had to shift it up a little bit because the plate was very close to this other plate, and I had to just move it proximally slightly. I had to move the whole osteotomy proximally slightly to allow us to be safe. Anyway, and this is him. This is 6 weeks later, walking actually in the middle of lockdown, 6 weeks post-op, really doing just fine. So I hope I've sort of talked through 3D imaging, the possibilities of smarter device manufacture without the stiffness that we've got at the moment, PSI guides to allow you to go perform surgery, possibly using 3D printed single-use instruments to reduce your inventory costs and your instrument costs and improve efficiency in the operating theatre. And then adding them all together, PSI and additive manufactured instruments, I think is a pretty interesting package. Thanks very much for your attention.
Thank you very much, Prof. Another excellent cutting-edge lecture from your side. Prof, just moving out of joint replacement, of course, you have mentioned all the great uses in joint replacements. Do you think we can 3D print bone into defects? For example, if you have a post-traumatic bone loss of the tibia of 6 centimeters, are we at technology so that we can really 3D print bone?
So if you, the answer I think today is no, honestly, Hitesh. At the moment, with a diaphyseal defect, basically you're either in the spatial frame camp or the internal fixation camp. If you're in the internal fixation camp, you're going to put something pretty strong in, and it's got to be strong. It's got to be left there, and because we know those diaphyseal lesions take a long time to heal, that you're effectively putting a permanent, right now it's a pretty permanent thing, and the cost of taking that thing out will be pretty high. So at the moment, I would say that's very, very hard. Very, very hard from the mechanical demands of that. You know, it's a young man fell off a motorbike, he's going to walk on it, you know, you won't be able to stop him. And the microbiology is the other thing. Very, very scary from the microbiology point of view. I think it is I think it's a very interesting project, and we're working in that space, but we're miles away from human trials, just miles away, because these very, very different conflicting variables. You want the thing to have disappeared completely, but it's got to hold a whole body weight until the bone's regenerated. And that's just such a hard combination right now. I think it's just too hard. So the other weird thing about being alive today is if you come up with a new material, well, you better be under 30 because the length of time it takes to prove a new material is safe is very, very long. These days, you just can't start experimenting with really, really, really new stuff. So we're stuck really with what we've got. And if you've got a highly porous bit of titanium, which is very exciting, interesting stuff, you'll never get it out. You will never get that out. So I think it's very interesting, but we don't have the answer yet.
And
Really?
are you able, yeah, Prof, thanks for that. The other question is, we look at most of the time, we look at what is a material that has the coefficient of elasticity more closer to the bones. And in such cases, we have looked at alum, we have looked at trabecular metal. So are you in a scenario that you can develop 3D printed trabecular metal?
Yeah, so that little video clip of Richard hanging from those push-in things, those little bristles, you can bend those bristles. So I do think this next generation of devices is going to be, I'm not imaginative to see beyond titanium and polyethylene and occasionally bits of ceramic. I think that's what we've got. I don't think it'll be cobalt chrome, it's just so stiff and people start measuring your metal ions. But with the additive layer manufacture, I think you can print stuff of any material properties you want. You really can. The challenge, honestly, Hitesh, is cost, because joint replacement now is so commoditized. You know, it costs this much, and that's how much it costs to cast a bit of, or mill a bit. Once you start doing things more expensively, someone's going to have to pay. And at the moment, I don't know what it's like in the subcontinent, but around here, if you say I want to use a more expensive device, well, you better have a big explanation for how much better it's going to be. You know, it's a real challenge, that I think.
It's good. It's the same everywhere, Prof.
Yeah, yeah.
I mean, cost is the biggest limiting factor.
So I think that the science and technology can deliver, but honestly, it's up to us to show. And I do genuinely think in the people with very low bone mass and skeletal failure, stiff bits of metal are not our friend. You know, we've all seen the fracture at the bottom of the plate, and boy, you know, you wish you weren't there. That's the miserable thing, isn't it? So I do think there's going to be a product or a suite of products coming out for those low bone mass old ladies who live forever. You know, they're never going to die, but if you put big stiff bits of metal in them, you're going to see them again, and it will get more and more difficult. So I do think that there's a real case for reducing the Young's modulus of the implants, and I think it has to. I can't see a way out of it being trabecular titanium or some modification of what we've got at the moment.
Prof, what has been your experience in the cost perspective with respect to these patient-specific instrumentation? Is it costlier or the same with the conventional instrumentation?
It really depends on how you do the business model. If you are running the Gopalan hip factory and you're doing 20 hips a day, and they're all on people who are cousins of each other, all the same shape and the same size, then the additive manufacturing doesn't have much to offer you because you've got it all there. If you're a lower volume center, then shipping 10 trays of instruments and the entire inventory of replacements for a case and then shipping it back again, that's an absurd cost that somebody has to bear. And actually, just a small box with only the instruments you need and only the device size you need, I think I think it probably is about cost neutral. The trouble is, both for the high volume center and for the company with a high volume practice that they're used to building trays and trays of instruments, then for them, this sort of product, it's too disruptive for them. They've got a supply chain running. If you've got the supply chain already, then you're not going to change your supply chain, I don't think. Whereas if for anybody starting up a company making something of their own, it's so much easier to do it this way because you haven't got to go and collect the instruments, clean them, curate them, sharpen them, all the stuff that, it's just too hard. Whereas with very lean manufacturing and just making what's needed, it's a low cost, it's a neutral cost, I would say. The PSI guides, because of automation, the number of minutes of human interaction with the PSI guides is very small. It's really very small. And so it doesn't have to be high cost. Of course, doesn't have to cost a lot to make. Obviously, for the people who are making them, they want to sell it for as much as possible, but that's another story altogether.
Thank you, Prof. I think there are no more questions. It was fantastic listening to you. Amazing research that you've been doing in the Imperial College. I'm sure it's going to benefit thousands of people across the globe. And we really look forward for the other cutting edge research that you do, like 3D print, augmented reality and robotics.
Another
Thank you
time.
very much, Prof.
Okay.
Bye-bye.
Bye.